Hi, in a previous video we took a look at a failure of a multi-layer ceramic capacitor inside a power supply module, and this is actually the second time this has happened to me, as I pointed out in the previous video, where the ceramic capacitors have actually failed short circuit and they've been across a high power source which has been able to deliver a lot of energy into that capacitor, and they catch a light. And needless to say, that can ruin your day if you're designing a product like this. So quite a few people have asked, and I thought it's quite worthy to do another video on this, actually looking in more detail of exactly what's happening here, and more importantly, what you can do to either reduce your chances of this happening, or basically eliminate it almost entirely, any issues when you're designing a product. Because this is, one of those more obscure things that you're not going to learn in school. This is like real manufacturing practicality stuff. So it's really fascinating. Let's take a look. So you can see in the photo here the before and after. Before, we had a multi-layer ceramic capacitor in there soldered between two pins, and that was the mistake here. Pins that have big screw terminals on them. So when you screw in those terminals on the other side of the board, you get transfer of mechanical stress onto these ceramic capacitors, and ceramic is actually brittle, so they tend to crack, get micro cracks in them, and generally these can fail short circuit. And that's exactly what happened here. The capacitor shorted, it dumped all the energy into that capacitor, and it caught a light, and, well, it ain't there anymore. But there's actually another two ways at least that these capacitors can fail. The other one is by thermally stressing them. You could have one end on a big ground plane, or both ends on a big ground plane, for example. On one end can matter, because when your board goes through the reflow oven, then the copper retains the heat very well. So if you've got one end of the capacitor, for example, hooked onto a large ground plane and the other one not, just going off on a tiny trace, that might impart thermal differentials, which can also crack your ceramic capacitor. So it's not as common, but thermal stress is one thing. Mechanical stress, which is what we're going to look at in this video, and the other is just infant mortality, manufacturing, issues caused by the component manufacturer. If you buy them from the Shenzhen market, you don't know what sort of quality you're getting. But even the good quality ones, it's just a manufacturing bell curve thing. You will occasionally get some outliers that could fail short and do a similar sort of thing. And I showed this table here of ceramic capacitor failures from NIC Components Corp, and it's a nice little summary of the different failure modes. Mechanical stress, as we're going to look at here, thermal stress, as I said, and those intrinsic defects and how to mitigate them. So that's just a useful table there. I'll have to link in the webpage down below to that one. So what's actually the problem here with mechanical stress? Well, this very handy graphic from the University of Maryland, their Center for Advanced Lifecycle Engineering, once again, I'll link it in down below, shows your multi-layer ceramic capacitor, and you can see the multi-layers. Sometimes they can have dozens and dozens or 100 layers in there inside, especially your really high capacitance ones, like people take for granted the 10 microfarad or higher, even 100 microfarad multi-layer ceramic capacitors. They're very modern technology, and they rely on very tight manufacturing tolerances with all these different layers of the plates in there, separated by the dielectric material, and they can be very fragile. They're encased in a ceramic dielectric material, and as I said, it can be quite brittle. So in this case, it's exaggerated, but if you've got your PCB and your capacitor's mounted on there, when it flexes like this, and the flexion can be due to as we saw in the power supply that failed, when you screw in the screw terminals on the thing, that can impart not huge stress like that, but just enough. You don't need much, tiny amount of stress at one end of the capacitor or both ends, and crack, because ceramic is very brittle. And you can actually see this is a micro cross-sectional photograph, 250 microns. You can see the size there, and you can see it's cracked right through the plates there, and that one's probably going to end up as an open capacitor, but they so very often fail as a short circuit. If they fail open, okay, your product might fail, but it's not going to catch a light and things like that. But if they fail short circuit and you've got it across a power supply input or output that's capable of putting a lot of energy into that, it can catch a light. So nasty. But yeah, this is what actually happens inside there. And it's very difficult to actually detect these things. And there's various techniques to do it. You can, cross-sectional cut them. You can actually measure. You can do an impedance analysis test, like flying probe test on the board and things like that. So you can get this board flexion from simply installing the board is one of them. You can get a drop. For example, if you've got a mounting post here and here, and your product is dropped, whoop, you'll get a little bit of flexion like that, especially if you've got heavy components like a transformer on there or something. Your board might do a flex like that, and bingo, you can crack your ceramic capacitors. Nasty. You could also have board plug-in connectors, for example. You got your mounting post here, you got your nice big Phoenix contact plugs or whatever. You plug them in after you've installed your board, and you can get tiny little flexion on there. You've no doubt seen this on computer motherboards and things like that. When you're pressing the RAM into the thing, you've got to squeeze it. That's putting stress on the board, and you can really come a gutser with that. Another way to crack them that you might not think of, after you've had them machine assembled, you may not do this yourself. It might just happen at the assembly factory. When you panelize boards like this, I've done a whole separate video on couple of videos on panelizing boards with routes and slots and V-scores and things like that. If you've got, say, V-score boards and you snap the boards like out, you've already assembled them, all your components are assembled on there, then you go snap the boards off, that can ruin your day as well. You can actually impart flexion in your board and crack your ceramic capacitors. So if you've got the slotted out boards like this, trying to push them out with your thumbs, for example, if you've got those breakout tabs, once again, imparting force. So that's why it's recommended to actually get the side cutters in there and actually cut out the boards from the panel so that you're reducing the stress on the board. So let's take a look at the PCB layout level and see how you can mitigate these sort of problems. And these things might seem obvious, but it's very simple to overlook these when you're designing boards and designing products. Please excuse the crudity of the model. Didn't have time to build it to scale or to paint it. We've got one capacitor on here and a connector, and we've got our 4 mounting posts here. And obviously, if you press the connector on there, that board is going to just flex a tiny little bit, and your capacitor is going to do the same because it's mounted in the middle. What can you do about this? Well, there's several things you can do about this. One is to have another mounting hole, for example. Whoop, there we go. You could have another mounting hole there, and it takes the mechanical stress away. So the first thing is just to stop the flexion happening, if at all possible, which means extra mounting posts and things like that. Put in mechanical connectors. You can move the connector over to here so that it's near some mounting holes if you didn't want to, have an extra one in here. If you've got the flexibility to do that sort of thing, then that can greatly reduce the stress or eliminate the stress on the capacitor. But let's say that you just had it like this. What's another thing you can do? Well, you can simply, like if you have a look at the board here, that's the 3-dimensional, so that when you can see that when you plug the connector in there, the board's going to flex a little bit like that when you plug it in, and your capacitor is on the axes like that. And that is the most you saw in the stress photo here, the stress fracture. They happen on the axes like that. So when the capacitor goes down like that. So what can you do? It's easy. You can simply, to reduce the stress on that capacitor, rotate it like that. So then you're not on that axis where it's where the solder points are like that, and when it flexes like that, if you know what I mean. If you rotate the capacitor like that, you're not going to get nearly the same sort of longitudinal stress, if I'm calling it the correct term, on the ceramic substrate, so it's not going to crack like that. You're just by simply rotating that component, you've already greatly reduced the stress on that. So if there are stress points on your PCB and you can't eliminate them for system design reasons or whatever, you can't put in extra mounting posts or whatever it is, then simply rotating your components can make a huge difference and probably eliminate the issue entirely. So let's take the connector out of the equation here for a second and say that you want to reduce the stress from the mechanical standoffs. You know, when you screw them in and things like that, that could be causing an issue, and your capacitor, for layout reasons, has to be right close to your mechanical standoff there. Well, what can you do about it? There's a simple trick. One way to do it is to add mechanical stress relieving slots into your board like this. So if we have a look at the 3D view, you can see that we've just routed out a slot in there. Don't worry about the little artifact there. A slot around your mounting holes like that, so that less mechanical stress is transferred through the board to your components surrounding it, but it still provides the mechanical rigidity. And by the way, multi-layer ceramic capacitors aren't the only electronic components to be susceptible to stress. If you get a really high precision voltage reference, you'll find that they are, it's quite common to find them actually surrounded by an isolation slot like this around the chip. They might come in an SO8 package like that, and if you see a slot routed around like that, it means that they're actually trying to isolate any stress, any flexion on the board like that into the chip, because the mechanical stress can couple into the voltage reference and it can drift and do all sorts of really subtle things. It's not going to ruin the chip or anything, but it accurate voltages references like this, thermal expansion of the board can do this, not only isolating mechanical stress but thermal expansion of the board. The FR4 material will have a certain value for its thermal expansion. For example, you can get different PCB materials with different thermal expansion coefficients, and that's a way to isolate components, but that's got nothing to do with the ceramic cracking and things like that. But you could, if you had to, isolate your capacitor with a slot like that, but that's that's pretty extreme. Generally, you want to reduce it using some other technique. So PCB techniques are pretty simple. One is to stop the stress happening at all, not only in the PCB handling phase, but also in the product phase. If you've got connectors and screw terminals and other types of things, just avoid that happening, or you can reduce the effect by mounting holes and just being aware of where the stress points are in your board. And third is to add isolation, mechanical stress isolation slots where appropriate on your board. And speaking of thermal expansion of the PCB, this can be a real problem, say, if you're designing a LED board, for example, LEDs on there. You might have an aluminium or other high-power components. A lot of a common thing to do these days is to have an aluminium-backed board so that it can be used as a heatsink substrate. Well, aluminium has a thermal expansion constant, and you can get thermal expansion issues on a aluminium-backed board like that. So you've got to be careful with the thermal stresses. They're a much higher coefficient than a fiberglass FR4 PCB that you're used to. So just be careful there. And just some other micro photographs here of some cracking, in this case an 1812 multi-layer ceramic capacitor. You can get the cracks running all the way through like that. I just love these. They're beautiful how they can get these photos. They can also show up on X-rays as well. You don't have to cut them in half to actually see this. But you can get pretty horrific stuff inside these brittle ceramic capacitors. The other risk mitigation technique you can do, I mentioned this in the video, is that you can put two capacitors in series. Yes, you halve your capacitance, but this increases your reliability, because if one that does fail short, then the other capacitor is there to take up the slack, basically. And yes, it'll halve capacitance when you put them in series, but then if one fails short, in your product will still continue to work as long as it can handle the double capacitance, because you're getting rid of one, so you double the capacitance there. So this is actually a very common technique for high reliability products, especially if your capacitors are going directly across a power source input or output, as we've mentioned. But unfortunately, this doesn't help you in the case of the capacitors failing open circuit, which they most certainly can. If either of those capacitors fail open circuit due to any of the mechanical or thermal stresses or whatnot, or the intrinsic failure of the capacitor, then that's not going to help you. Your capacitance is going to vanish, but at least your product is not going to catch on fire. So the way to mitigate that, of course, would be to have two of them and then another two in parallel with that, but that's getting pretty extreme. And another technique is to simply use smaller size capacitors. The smaller you go, the less flexion overall you're going to get for a given unit length. So, some people might have a blanket rule. I'm not going to use bigger than 0805 ceramic capacitors, multi-layer ones, for example, because of the extra risk. The larger the component goes, you go to 1206 and then bigger ones, you get some of the real monster size ones, then it doesn't take much flexion at all to actually crack those. So the smaller ones, they could be a valid reason for going for those 0402s. Now, of course, another obvious technique to eliminate this sort of multi-layer ceramic capacitor shorting problem is to simply not use multi-layer ceramic capacitors, and sometimes that's an option. You might use a film type, you might use a tantalum, or something else. But multi-layer ceramic capacitors are very popular for the reason that they're incredibly, the volumetric capacitance per unit volume is incredibly high, and they're cheap, they're surface mountable, everything else. Yeah, they got downsides, they're microphonic, as I've done videos on, and they're susceptible to cracking and stuff like this, but they're used for, very legitimate reasons. But you could, in high reliability products, like directly across the mains, for example, you might use a film type capacitor, your X2 rated caps, for example. But there is another option. There are companies that actually manufacture multi-layer ceramic capacitors that are intrinsically safe and certified. Seifer is one example here. They've got a flexi cap thing. They're certified for, your X and Y capacitors go directly across the mains. Once again, there are mains is an incredibly high energy source, so you want certified capacitors to go across there, and they actually offer a range of these certified, they're tested by, approved by UL and TUV and everyone else under the sun, rated for directly across these supplies, and they are multi-layer ceramic capacitors, and they use this using flexi cap technology. And there's other companies that actually, AVX, Kemet, there's a whole range of, almost every legitimate capacitor manufacturer on the planet is going to offer specific multi-layer ceramic capacitors that solve this very specific problem. So let's have a look at TDK here. They're another manufacturer of components that have, this flexi type technology that can help reduce or practically eliminate the issue here. Now, if we have a look at this, they've got these, they put the multi-layer ceramic capacitors on what's called a mega cap. They're the lead frames, and I've showed this in a previous video, and the lead frames on there, they can actually take the stress. And you can actually see here that compared to a regular capacitor, this is the flex amount in the board here, and I'll show you the standard for that in a minute. The flex amount in millimeters compared to the cracking in the thing, and it needs, like, they start cracking at like 4 millimeters flexing and things like that, whereas using this technology here with adding these little lead frame things in, then you can basically get up to 10 millimeters of flex in the board with no cracking whatsoever. And there's actually a standard for this. It's AEC standard. It's an Automotive Electronics Council Q200. 005 is the specific one for flexion of the board here, and they, like, the supports like this are 45 millimeters out. This is the standard. When they talk about flex, generally that it can survive, this is what they're talking about here. So, a little weight comes down on the supports and how much they flex by, and that's how much they can actually survive flexing. So just mounting that alone can practically eliminate all of your issues here. And here you go. The mega cap features absorbs stress of the board flexure by its unique metal frames, can be mounted on aluminium circuit boards. Beauty, provided with metal caps that absorbs the stress caused by mechanical shocks, and in a flexure it's not just shock. Also features improved vibration resistance as well. They can, so that's talking about microphonics there. They might be able to reduce or change the resonant mode of the microphonics if that's a problem. And you can get more capacitance because you can physically stack them with these lead frames, and they got lower ESR and ESL etc. But yeah, there you go. So very common in automotive applications. And another type, if you don't want to use those lead frame types, because that extra process, they might cost money or whatever, you might not be able to afford the height, whatever, is to use these soft terminations. You can see in this particular case, all the manufacturers will have their own technology and ways of implementing this, but they actually have a conductive resin layer inside there. So that actually takes the stress, decouples the stress from the mechanical end caps to the ceramic dielectric, yet it still allows the conduction through. So it is really quite neat there. And you can see, once again, they can flex up to 10 millimeters with these soft termination technology. It's not going to cause a problem. Beauty. And you can actually see here, it doesn't stop these things cracking, but what it does, you can see on the left-hand side here is your traditional multi-layer ceramic capacitor, and you can see that there's a big stress crack right through there. It's horrible. The soft termination ones can still crack, but they don't crack the ceramic dielectric inside. Yeah, it might peel off a little bit, but you still got that conductive epoxy type stuff in there to go through. So there you go. Just terrific technology. And this is such a serious problem that the manufacturers have had to develop very specific component manufacturing techniques to reduce and eliminate this sort of problem. It's a big deal. But in this particular case for this soft termination TDK technology, you can see that basically the main disadvantage, apart from probably extra cost to manufacture these things, is, you know, a 12.5% decrease in nominal capacitance, volumetric capacitance or whatnot. But that's a small price to pay for having a reliable product. And some markets, like the automotive and other high vibration, high stress environments, demand this sort of reliability. And this is an interesting graph here. Using this soft termination technology, the amount of cracks, issues per number of times dropped. Look at, you know, the regular multi-layer ceramic caps just go up and up and up the more times you drop them. That mechanical stress can add up to a point where, you know, you might start with a little micro crack, doesn't damage your product, but then that can get bigger and that can provide a crack point to make it bigger. So every time the product is dropped can cause an issue. And well, if you get your capacitors from the One Hung Low company, their stall at the Shenzhen market, you know, and you need a reliable product, well, that can cause a big issue. So, but if you spend the money, you can buy the capacitors that are super reliable like this. And the other way to do it is you can actually TDK sell these capacitors that are effectively two capacitors in series in the one case. The way they've arranged the layers in there, as you can see, it's basically an arrangement of two serial capacitors in there. So you get the volumetric size, it's probably going to be decreased. The capacitance is going to be decreased, but you don't have to have two physical components which take up more size when you've got the footprints and everything else associated with them. But once again, if these things don't have the soft termination technology or the lead frame technology, they're just simply a lower cost, more reliable version that prevent the short-in capacitor problem. These things effectively will fail open if they're going to fail. And another way you can guarantee, from a manufacturing point of view, that you can get these to guarantee to fail open is that you can actually extend the length of the materials inside. So this is all part of the manufacturing thing. Once again, the data sheets will probably, I don't know if they guarantee it, but they will say, you know, like it's almost guaranteed to fail open. The risk of it failing short, because the cracks usually happen at the end terminations, as we've seen in there. So if you move the plates back from the edges where the cracks typically happen, then you practically eliminate the possibility of a short, because it just, you know, it physically can't happen. You can see down here, this crack goes down here. A regular one can actually short out the plates, but this one can't because they don't overlap until they get further within the chip. So that's pretty neat. So here's a nice little summary of TDKs, 4 different, you know, one technique is not perfect, so they need 4 different techniques to mitigate the problem of flex causing cracks in issues and shorts in multi-layer ceramic caps. So the mega cap, the soft termination, I'll let you read that. But, you know, cost, obviously the open mode ones are the highest cost. Look at that. I wouldn't have thought so, but obviously they need larger ceramic material to actually do that, and they're going to be physically larger on the board as well for a given volumetric efficiency and stuff like that. So the cost, the smallest one is simply the lead frame, because they just take their existing capacitors, which are already manufacturing in the quadrillions, and they just solder on some little lead frames on the end. The other ones are soft termination and the series design. I'm surprised the soft termination is actually, isn't right up there in the highest cost, but I guess they've perfected the technology that it's not too bad. So we'll just have a very brief look here at the end of this TDK soft termination technology. Look at this. It shows you a very nice little diagram of how they actually do that, the conductive resin layer and everything else. So I was just wondering what's the cost difference here between these and regular ones? Let's take a quick look. Now, if we go on Mouser here and actually have a look at a specific TDK part number for a 1 microfarad 0402 multi-layer ceramic capacitor with soft termination technology, here we go, 2.8 cents in 10,000 quantity. So if we go over here and just find an equivalent, just a generic one, but check this out. This is interesting. The Mouser parametric search actually has the termination type, a specific soft flexible termination. And of course, if you choose that, then only the TDK parts will show up, because that's a specific TDK thing, and they've put that into the parametric search. But that's really quite useful, isn't it? I like it. But anyway, if we search for all the catalog for 1 microfarad 0402 capacitors, sort by price, we're looking at 1.3 cents there. So basically half the price. So basically it doubles the price for that in volume. 10,000 is a reasonable volume for that soft termination technology. So there you go. And if you use some of the other ones, they are more expensive again. But yeah, that's double your cost. But if you've got a lot of caps on your board, that can really ruin your BOM cost and ruin your day. But something like an automotive product, reliability is the number one thing. So they're not going to skimp on cost. They're going to specify that specific part number. For example, it must be that, no substitutions, and that's it. Right, they must buy it, and they buy it from the original, a reputable certified source. So make sure they don't get any, no substituted crap quality parts somewhere in the supply chain or something like that. And they would pay double or even more for these, especially if you got big ones that are, like equivalent to like the film capacitors, the X1, the Y1 kind of ones that go directly across the mains. They could cost a lot more or whatnot if you wanted the volumetric efficiency of the multi-layer ceramic capacitors, but you wanted that reliability and guaranteed certification, you'll pay for that. Anyway, there you go. I've waffled on long enough about cracks and micro cracks and shorting and how to reduce those in product design for multi-layer ceramic capacitors. It really is a big issue that all the major manufacturers out there have solutions to solve this specific problem. So I hope you found that interesting. If you did, please give it a big thumbs up, and I'm sure I've missed some things. There's other techniques you can do as well. It's probably not entirely comprehensive. But anyway, I hope you found it useful, and as always, discuss down below, and there'll be links to various application notes and data sheets down below. Catch you next time.